Hi, I'm Anurag Sarkar from Northeastern University, and in this presentation, I'll be talking about work done with my co-author Seth Cooper, where we introduced a fully online system for dynamic difficulty adjustment in human computation games via the use of player versus level matchmaking. So, human computation games, or HCGs, are games whose levels model real-world problems in order to help have them solved by using the collective abilities of players. So, games such as Folded, where levels model protein folding, or one of the games that we used in this work, Paradox, where levels model constraint satisfaction problems, are some examples of games in this category. And performing dynamic difficulty adjustment in these types of games is hard because you can't really modify the levels, because then you run the risk of breaking the connection with the underlying problem that you're trying to solve. And so, in some of our prior work, we have looked at difficulty balancing in these types of games using player rating systems and skill chains. So here we frame the DDA problem as one of player versus level, or PVL matchmaking. So a player's rating indicates how good the player is, while a level's rating indicates how difficult a level is. And then with these ratings, a rating system such as ELO, or in our case Glyco2, can be used to matchmake between players and levels, which results in players being served levels that are appropriately difficult for their current skill. Additionally, skill chains give us another type of this progression-based method of difficulty adjustment. So skill chains define the order in which players acquire skills during gameplay, and this order of skill acquisition can then be leveraged to define level progressions of different difficulties. And so in a prior work, we combined the use of rating systems and skill chains to form this DDA model, which at a high level works in two broad steps. So in step one, the skill chain of the game and the player's acquired skills are used to determine the set of eligible levels. And then in step two, the rating system determines from among the eligible levels which one is the best match for the player, and then that level is served to the player. Now, while this model has been shown to be effective for difficulty balancing in HCGs, it does suffer from a couple of issues. So first is that level ratings need to be gathered in a separate offline phase prior to matchmaking via a large number of playthroughs of levels served randomly, and then after that these ratings have to be held fixed during the actual online matchmaking experiment. If we start these level ratings from a default value and try to update them over the course of matchmaking, we end up encountering this cold start issue where level ratings don't accurately capture the difficulty of the level. So we run into situations where the more difficult levels are played mainly by the more advanced players, and so these levels end up with lower ratings because of the skewed distribution of players that played them. And an additional problem, what is more of a limitation, is that each level needs to be assigned a target score threshold in order to determine wins and losses, and this is kept constant across players. And what we'd like to do is perform more fine-grained difficulty balancing and set these score thresholds dynamically for each player versus level match, rather than set the threshold and have to keep it fixed during matchmaking. And so our solution to these two issues was first, we used a simple epsilon greedy matchmaking strategy to address cold start by allowing players to be assigned random levels in certain situations instead of levels via matchmaking. This helps even out playthroughs so that levels are more likely to be played by both advanced as well as novice players. And second, we incorporated the concept of level rating arrays, which we introduced in some of our other prior work. And here, the basic idea is rather than assign a level a single rating, we assign an array of ratings with each rating in the array corresponding to a different score threshold for that level. And this allows us to set a level's target score dynamically by comparing a player's rating with the ratings of each threshold. And for our experiments, we use these two human computation games. So on the left, we have Iowa James, which is a side-scrolling platformer centered around item collection, where players have to collect items belonging to a given category while avoiding those that do not. And on the right, we have Paradox, which is a 2D puzzle game where levels model Boolean maximum satisfiability problems, represented as these graph-like structures, and players have to satisfy constraints by assigning true and false values to variables. So first we have our epsilon greedy matchmaking algorithm, and the central idea behind it is just that with low probability, we serve randomly chosen levels rather than levels chosen by the matchmaking system. And this helps even out the distribution of players encountered by each level and correct for the skew as described previously. Now, since the matchmaking system works in a two-step process, namely determining eligible levels using the skill chain and then using the rating system to determine precisely which level to serve, we use two different epsilon values. So we used epsilon 1 to determine if we should serve a level completely at random, so using neither the skill chain nor the rating system. And we used epsilon 2 to determine if, having already determined the eligible levels using the skill chain, if the levels should now be served randomly from among those, or if we should use the rating system as per usual. So we had these two different ways of randomly serving the levels. So to test this algorithm for each of the two games, we recruited players using Amazon Mechanical Turk and assigned each player to one of four settings of epsilon values. To keep to a manageable number of conditions, we used the same values for both epsilons, and so we had epsilons equal to 0, which was the same as using the original DDA model because there's no randomness in that situation. And we also had both epsilons equal to zero point 0.1 and zero point 0.2, and a final condition where both epsilons were set to 1, and this acts as a complete random model with no matchmaking. In terms of variables, we looked at playtime, levels completed, levels lost, and level rating error. And the last of these is the mean square error between the level ratings that were encountered in each condition in the matches versus the final level ratings that were obtained in the random condition. And the reasoning behind this is that in the original DDA model, the level ratings that we use are gathered via offline random playthrough, so it's not unreasonable to use the level ratings obtained from the random condition as a proxy for the true ratings for the levels. And so moving on to the results, as expected, random had the lowest level rating error because as I just mentioned, using random playthroughs tends to produce more accurate level ratings. But the more important results here are those obtained for the epsilon equals 0.1 and zero point 0.2 cases, where we see that for both of these and in both games, we obtain lower level rating error than the original model of epsilon equals 0. And additionally, the levels completed was not significantly lower compared to the original for both these cases. And so the takeaway here is that this online epsilon greedy approach produces more accurate level ratings compared to the original, while still being able to do useful matchmaking, as evidenced by there being no negative impact on the number of levels completed by the players. And so overall, this points to this epsilon greedy method being useful for allowing us to do this type of player versus level matchmaking in a fully online manner. And so that brings us to the second extension to the model, namely level rating arrays, which is a concept that we introduced in a prior work of ours, but this is the first time that we actually used it in a live setting. Now, we don't have time to go into details regarding how exactly these arrays work and how matchmaking updates are performed using them, so for that, please consult the paper, but briefly, the idea here is instead of assigning a single rating to a level, we assign an array of ratings to each level. And sort of similar to how a single rating would indicate how difficult it is to complete a level, each rating in the array here indicates how difficult it is to complete the corresponding percentage of that level. And doing this now lets us compare player ratings with each of these thresholds, and in turn lets us determine what the appropriate threshold is for that player and set it accordingly. And so we no longer have to keep this threshold fixed for each and every player. And in the experiment, for each level, as shown in the slide, we used an array of 10 elements corresponding to evenly spaced scoring thresholds of 10% apart. So again, for this experiment, we recruited players using Mechanical Turk and randomly assigned them to one of two conditions, either using the rating arrays or not using them, that is, using a single rating per level. Note that for this experiment, we only used paradox because it has these levels with well-defined notions of partial completion, such as, for example, 10% completed, 60% completed, whereas that is harder to define for the Iowa James levels. Also, we used epsilon equals 0.1 for both conditions because that had the best results in the prior experiment. And we looked at playtime, levels completed, and levels lost. Additionally, we also tracked the high score for each of the 19 non-tutorial levels in the game. And we found that players in the array condition completed significantly more levels than those in the non-array condition. And for our high score evaluation, we did find that the non-array condition produced higher scores for 8 of the 19 levels, but these differences in high scores between the two conditions were not found to be significant. And so the takeaway here is that the rating arrays can lead players to complete more levels while producing similar high scores as the no array condition. And this is quite interesting because the array approach likely produces significantly more completions on account of tailoring the target score thresholds to make the levels easier to complete for some of the less skilled players. However, even with these lower target scores, players were still able to attain high scores that were comparable to those in the non-array condition. So in conclusion, we presented an online version of a prior DDA system, which was enabled by using an epsilon greedy matchmaking strategy to address a cold start issue that previously made this infeasible. And we also demonstrated the first online application of rating arrays for matchmaking, which was shown to help players complete more levels. In the future, we'd like to be able to automatically infer the skill chains, develop probabilistic models of player skill acquisition, as well as test rating arrays with other HCGs and educational games. That concludes my presentation. Thank you.